Good afternoon, everyone. Here is Dave Tulloh. He's going to talk about Kicad. How's it pronounced? Kicad.
Is that decided?
I read online that it's pronounced Kicad, and thus it must be true. Up until yesterday, I've always pronounced it as Kicad. I'm going to try hard to say Kicad rather than lead you guys down the wrong path, but I might get it wrong. It does run on Linux. Right at the start, if you have not installed Kicad, please do so now. You will need it. Could you hand that out to everyone, please? I will go through what that is for as we go. So just in case anyone is in the wrong room, this is a tutorial. It's 2 sessions. I have structured it in 2 halves so that if you want to leave halfway, you can do so, and actually people who come in at halftime can join in. It is a tutorial. I am expecting you to play along. I'm following the principle that the best way that you learn to do things is by doing them. Most of the time is going to be you guys doing stuff on your laptop, which has the lovely side effect of it's not me doing stuff. For the people watching at home, the tutorial really is designed for the hour and a half and the people in the room. If you would like a tutorial, I'm sure there's better ones online designed around being able to pause and rewind and that kind of thing. There's probably going to be a lot of dead time from a video perspective in this session. So what we're going to be covering is I'm going to give an introduction to schematic drawing, and then you will do a schematic drawing. Miles has just very kindly handed those out. I'm very explicitly not going to be covering how to design a circuit. We have nowhere near enough time for that. So I've designed one for you, which is what has been handed out, and we will just be putting that into the schematic program. That'll be the first half. The second half will be converting that schematic to a PCB to the point where it can be constructed. Yes, anyway, that's the plan. When starting this project, I needed to come up with a thing because we're building something, it has to do something. And honestly, for this process, it's a little bit arbitrary. But what I've decided to go with is a sprinkler system. So garden sprinklers have systems which allow electronic control. That is a electronic valve that you can buy from Bunnings. I bought one to use as a prop, and then I left it at home because life's like that. That one's easier to see anyway. So they're electronic control. You can buy existing controllers, some of which are a little bit fancy, some of which are basically timers. I mean, they're all basically timers. We're not going to do that. We're going to build our own controller. And to keep things a little bit contained, we're just going to control a single unit. You might be able to read on that that it's got 24V. That's the power that it takes. So the system that we're going to be building looks a little bit like this. Essentially, we've got the valve, we have a power. Sometimes we want the power to be on, sometimes we want the power to be off. So we're going to take the power from an external power brick. We're going to run it through a switch, and it's going to go to the valve. The switch has to be controlled by something. We're going to drop an ESP8266 Wi-Fi controller chip in because it's nice and easy, and then that needs some level of power supply, which we're going to steal off the 24-volt input. This is made a lot more exciting by the fact that the valve runs on AC power. and AC power sucks. So what we're going to be going through here is I'm going to give an introduction. Hopefully it'll go for about 10 minutes. Then you guys are going to be working on building up the schematic diagram. I will then wrap that up in about 5 minutes, and we'll put the finishing touches on that, and then move into the PCB section, which will be much the same again. So this roughly plots out to 30 minutes producing the schematic, 30 minutes producing the PCB, and 30 minutes of me talking. Very quickly, a little bit about me. I'm an electronics designer. I've found someone, for some reason, currently willing to pay me money as an electronics designer. I am not a Kicad. That didn't last long. I am not a Kicad developer. I'm approaching this very much from the user's perspective. I've used Kicad for electronics design. I've used proprietary programs for electronics design. The goal here is really just to produce a product at the end, and Kicad is very capable of doing that. I'm also, when I wear different hats, a software developer. So one of the things that I'm trying to do in this talk is use software analogies instead of car analogies, because I don't know much about cars. And I'm also going to be trying to bridge the mental model that a software developer has across to electronics and take advantage of the way that you as software developers already think to make you electronic designers more quickly. If you are not currently a software developer, some of the jokes will fall flat, but that might not be so bad anyway. It's certainly not a requirement for what we're doing today. So, what is a schematic? A schematic describes how an electronic product works. It is an abstract depiction. We talk about connections, not physical wires. We're connecting symbols, not physical parts. There is a link between the two. It's a relatively close link, but we are thinking abstract. Essentially, we're doing source code. We're not writing a binary. So just sort of keep that in the back of your head. This process is writing the source code, which will then be compiled into our final product. Demo time. Okay, so the demos are going to be following what's probably a slightly unusual structure. This is something I've drawn from a course I've done fairly recently. What I'm going to be doing is first I'll go through and I'll just show you how it's done. It'll take a minute, probably less. The idea is that you can see it done, you can get an idea of it, get a taste of it. Not expecting you to really understand at that point. It's simply seeing it done. Then I'm going to go through it again, the exact same process, and I'm going to explain every step along the way, so that you then understand what's happening. And then I'm going to ask you to do it. Please help each other out. And for most of the time, I will try and circulate and see if anyone has any problems. If there is a particular thing that's holding people up, I'll address it to the group. If everything is going smoothly, I will share insights and funny stories as you're going. Okay. So, when you run Kicad, this is what you see. This is the launcher, essentially. Kicad is actually a number of separate but tied programs. So, new project. So I'm going to open up the schematic file. Let's just put you somewhere else. So this is just me demonstrating at the start. Okay, that was exciting, wasn't it? Excellent. So if you look at the piece of paper, you can see that I've reproduced the segment on the right-hand side in the middle. I'm not quite finished. Yep. Okay, yeah, done. So that's what we're doing. That's the process. It is unfortunately about that exciting. That is a portion of the circuit. The way I would recommend you think about it is that is a function, right? That is our switch that achieves a particular goal. It has inputs, it has outputs. Each of those independently standing sections on your piece of paper is a different function. And then we effectively use globals to link them all together. So I'm going to do that again, and this time I'm going to talk through exactly what I'm doing. So the first thing is I'm using keyboard shortcuts. I've given you a list of the keyboard shortcuts on the piece of paper down the bottom corner. I strongly suggest that you start by using the keyboard shortcuts. The CAD program is really designed to be used with one hand on the keyboard in that fashion. So the first one that's important is zooming in and out is done with F1 and F2. This is a little bit exciting. The best way to navigate the document is by zooming in and out. It will zoom in where your mouse is. So if I were to move the mouse up, I zoom in, it recenters. If I wanted to go to a different portion of the document, I zoom out, I recenter my mouse, and I zoom in again. CAD programs all have their own special way of working. There's no point fighting it, you will lose. First thing I do is I add my components. I press A, and a component list comes up. I just start typing into a search box. So this is Q1. If you look at the list on the left-hand side, there's a list of all of the symbols which are used. So Q1 is transistor FET FDS 6890A. So that's a type of transistor. So if I just type that in, I get that. It's actually giving me at the top, it's giving it to me immediately because I've just used it. So we have that. I push OK, and I have a part. and I just put it down. I just left click, and I put that down. I press A, and then I'm selecting unit B of the same part. So this is one chip that has two transistors. So we have A and B. There. Anyway, to get the positioning that I want, I can move this around. I push Y to mirror the part around the Y-axis so that I get the layout that I'd like. I left click and I drop that down. I go over with the mouse to the gate terminal of the transistor. I press W for wire, and I run that across, and then I left click, and that's how I connect two parts of the transistor. I come down here, I press W, run that down, left click. Because it's not a terminal, an end point, I can keep going. I left click, put a corner in, left click to end it. I'm going to do that again up here. So you should be able to see the pen icon on my cursor. I'm still in wire draw mode, so I just need to left click. I run the wire up, left click, run it across, and then I double click to end the wire. And that creates a terminal at that point. And then I'm going to start drawing the wire again, left click, click, and click to end. The next thing that I'm going to do is I'm going to add my variables in. So these are essentially the arguments into my function block. We call them net names because each of the groups of wires is called a net. And I'm going to put a net label. So I press L, and then I just type what I would like in. Much like programming, there's a convention. The convention is to use all caps. And I'm just going to call that valve. It's a variable. The name doesn't actually, you just choose something that means something. So VAC is our AC power input. There's VAC1, VAC2, because there's AC, and there's no really nice way of naming it. What I'm going to do down here is going to click. Oops, sorry, I'm in label mode. I press W to go to Y mode. I'm going to run a wire up. And the reason I'm doing this is to make it very, very clear that this net label goes somewhere else. Much like source code, you want to write the code in a way that makes it clear at a glance what's happening. If I was to put the label just on a wire that goes between two places, it's not clear that it's going to go somewhere else as well. So I'm going to put it here, press L, label, and we call that switch 1. We don't really need the 1 actually. Anyway. And finally, I'm going to put a ground port on the bottom. Power, this is it's a net label again, but it's got a symbol for it because symbols are nice. It's the same technique. I just type in G and D for ground, get the part, left click to put it down. Are there any questions at this point? Does this make sense? Question?
Did you have to place the cursor on the wire before you added the label?
No, don't think so. Let's see, if we just go, no. So it's attached to the cursor, and it'll wave round, and then when I left click, it'll drop it down.
How is that being associated with the wire?
The label.
Yeah.
You see there's the crosshair there. So when you drop that on a wire, that's now associated. I should mention, if I push M for move, to move a part, you hover over the part, hit M, so I can move that label, move it across. If I push it there, you can see it's put a little box, much the same as at the end of the wire. I'm pointing at my screen, I don't know why. So the little box just under the AA, that's a hint that it hasn't connected to something. By convention, I always run the wire the full length underneath it. It's really not necessary, but it looks better. And we're making pretty pictures. So give it a shot. Try and space it out a little bit more than I have on the A4 page. You aren't nearly as constrained for space. But yeah, give it a try. Sorry, if you're in Y mode and you'd like to escape, or any other mode and you'd like to escape, press escape, and it'll take you back to the default select mode. It was pointed out to me, everyone seems to be going really well, which is fantastic. It was pointed out to me that I missed a step in my step through demo. What I'm doing with a few of the parts is like the transistor, is I'm using a generic symbol, and then the part number is slightly different, partly because the part in the library is old. To update that, you just double click on the text comment, and then you can type in the full one. So this is a full part number, and then I'm just going to hit copy with Control C, double click on that one and paste again. Something else that just wanted to make clear, I've left it as Q?A and Q?B. Please do that. Right at the end, we'll number the whole sheet, and that'll all get done. The sheet that I've given you has the numbers so that you can cross-reference the parts. Anyway, everyone's doing fantastically. Please keep going. So there's been a couple of people who, as they're progressing, need to move large amounts of stuff and restructure things slightly. So I thought I'd just quickly show that. So if you select with the left mouse button, it will select a block, and you can move that block. So if I do this as a demonstration, select the left mouse button, move it around. It's a little bit more complex because the behavior is slightly different if you select from the left to the right or from the right to the left. So to demonstrate that, I'll use this top area. So selecting from the left to the right, if I select a box like so, or I've deliberately selected only half of U1, I might have just misled everyone. I'm very sorry, I'm getting confused between my programs. So yes, if you select, it will grab anything that is partially selected and let you move it around. If you hold down the delete button and then select, it will actually delete everything that it touches. And the only other, I have to press Z. The only other tip is often copying using C is faster than adding a new component pressing A, just to make life a little easier. No. Hi. It's a bit of a shame to do this. Everyone seems to be doing really well and progressing really well. Unfortunately, we've about reached the halfway point, so that we have enough time to really get into the PCB layout. We're going to have to move on. So I'm just going to show the finishing steps for the schematic, and then I'm going to ask you to download the schematic file so that you can progress into the PCB. So for starters, if you could go to GitHub, github.com/LOD/LCA2020. That is where the files are, and you can grab a complete version of the schematic from the Electronics Complete Schematic folder. If you just grab the schematic file and rename it, that should be sufficient, or you can grab the whole lot. How do we do this one? To wrap up, so the final steps on the schematic, and feel free to follow along. Sorry. The URL is github.com/LOD/LCA2020. That one is a little bit bigger. I'll just leave that up for a moment. Okay. So the wrapping up steps of the design, I'm just going to break a few tiny bits to show what's going to happen. Not that bit. Get rid of one of those. Okay, so the first thing when you're finished is you annotate the schematic symbols. That's the pen thing up the top there. There's a few options around the annotation, but essentially you just click the annotate box button, and all of the parts now have numbers on them. So if I zoom in, you can see this is now D4, R5, R6, and it's just numbered them from the top corner moving forward. You're welcome to join us if you'd like. Nope, he just ran away. The second step that's performed is an electrical rules check. This is like a lint check for the device. So if you just hit run, it comes up with a couple of errors. These are sort of the most common types of errors. The first one is the pin's not connected to anything. So that's question. The little ladybird bug button on the top. So these are two most common that you're likely to see. The first is a pin's not connected to anything, and it thinks that it should be. And the second is that there's no driving source for the pin. It's got a bunch of inputs and there's no output telling it to do something. So if I hit close, you can see there's a little marker. This one's better. There's a little marker there saying that that pin is a problem. That's the I'm not connected to anything pin. What we do is essentially tell the linter that it's all okay. So if I just the X on the side there, and I put the X on it, that's essentially me just telling it to suppress all warnings on that pin, which is not fabulous, but it works. The other problem you can see is up here. You have a input on the VIN line, and it doesn't recognize that there is an output because the bridge rectifier it views as being passive rather than as a power source. So you might have seen on the diagram that I gave you, there is this power flag symbol sitting there. So this diamond is a way of Kicad saying that this is a power supply. So there's one here saying that the bridge rectifier is acting as a power supply, is delivering power to this segment of the network. And you can see there's actually one on the ground as well, because the ground is a driven source. So essentially the bridge rectifier is driving both the DC power and the ground. And then finally, we push the next button along, and we assign footprints. And the footprints are on the back of your piece of paper. If you have downloaded the file from the internet, all of those footprints should be set. I will very quickly point out how to use the footprint selector, because it is a little bit exciting. The footprint selector has a bunch of footprints, footprint libraries that you can choose footprints from. And then there is a bunch of, because there's a large collection, you can filter. So you can see on the right-hand side that there is a lot of footprints in that list. If I push the filter footprint list by library, then the panel on the left starts actually doing something when it wasn't before. So now we're just seeing battery footprints. If I go down and I select capacitor surface mount, you have the capacitor surface mount footprints. There is a search box. I can type in the search box, say 5.4, and it does absolutely nothing until I push the little button next to it that says filter footprint by partial name or pattern. And now it's filtering both by the library selected on the left and the search thing. And if I want to, I can remove the filter by library, and it'll get me every footprint with 5.4. This is a little bit odd, which is sort of why I pointed it out, but it is usable. So has everyone downloaded that schematic file? If you'd like to use your own, and if you've finished, that's fantastic. Go for it. So as I was circulating, people are making great progress, but not many had seemed to get it done.
I've got many more design rule failures.
I can come down and have a look.
Can you give us the URL one more time?
The URL is github.com LOD LCA 2020. And you want the electronics complete schematic folder.
You only need an SCH file for that?
I think so. If it opens, just rename it. If it opens, then we're good.
It's over the top of mine and reopen.
Yeah. Yep. Over the top should work. Okay. Nope. Some people are still looking at the thing. While people are downloading it, I will go through a few slides. So we've wrapped up the schematic, we've annotated it, we've done our design rule check, we've set the footprints. Quick introduction to PCBs. Converting the schematic to a PCB is a compilation process. We are compiling our source code to a distributable product, and the best part of it is we get to do the compilation ourselves. Because we're building, so this is a PCB. I'm sure everyone pretty much knows. This is actually a 4-valve version of the design that you've just been working on, which I knocked together, and I got these PCBs manufactured recently. I thought I would bring them down and wave them around, and then they got delivered on Monday. But they look pretty, don't they? So that's a PCB. Very quickly, I'm going to go through how a PCB is made, because I think having a basic knowledge of this actually makes the process make more sense. These images have been borrowed from eurocircuits.com. Eurocircuits is a PCB manufacturer in Europe. They have a fantastic description of how PCBs are made. It goes into a lot more detail than this. If you want to learn more, I would encourage you to go to their website and have a look at that. It's so good that quite a number of other PCB manufacturers have copied it wholesale. Generally, they remove the watermark. So this is a PCB core. This is a sheet of fiberglass with a copper foil glued to the top and the bottom. Generally, the PCB manufacturers buy these sheets from a dedicated core factory that produces them. This is the starting point. We are going to do a 2-layer design, which means we have 2 layers of copper, one on the top, one on the bottom of this fiberglass core. You can get 4-layer, 6-layer, 8-layer. 4 layers quite common. The manufacturers claim that they can do 50 layers these days. For some reason, would be very expensive. Kicad can support 32 layers, I believe. Ballpark, it costs you about $100 US to add a pair of layers in small quantities. So once the manufacturer has that sheet, the first thing that they do is they drill a bunch of holes. The diagrams from here are a 4-layer board. I'm sure it'll make sense. So essentially, they take the board, they drill a hole through it. They then plate that hole with copper so that it's copper going through. The important thing to note is that the copper is connected to the top layer and the bottom layer through the hole that has just been made. Then they etch away the bits of the copper at the top that they don't want. So what's left is called a trace. That's essentially a wire. The hole we call a via. So it's a wire to a via, which can do things. Then a solder mask is added to the top and to the bottom. The solder mask is most commonly green, but you can get them in black, purple, or red, whatever color you'd like. That controls where the solder goes on the board. So it's only going to put solder, the solder is only going to make contact with the exposed portions. The green protects the rest of the board from getting solder on it. The board is then plated because copper oxidizes very quickly in the air. So this is showing an ENEG finish. That's a nickel and gold plate. The cheapest plate is called Hassel. Hassel essentially involves dipping it in molten solder. And there's silver and a few other things, but plated. And finally, they apply a silkscreen layer. These days, they just use an inkjet printer. It's a little bit more expensive than this inkjet printer, but they just print most commonly white text onto the top of the PCB. So that's what you get. And if I just go all the way back up. So that's the final product. You can see it's got the green solder mask. It's got an hassle coating, so it's been dipped in solder. And you can see the white text of the silk screen. And the traces is the lighter green, where the copper is still present. That's the wires running across the board. So that's what we're going to produce. The task that we do is quite similar to the way the schematic was done. What you do is you position the footprints for the parts. Each footprint defines its copper pads, it defines its solder mask, that kind of thing. It's all done for you. Then we define the traces and the vias to connect those footprints together. Finally, we position and the part labels for the silk screen. Demo time. From the schematic, there is a green PCB symbol, and if you click that, it runs the PCB editor. Interesting. Exit without save. I am just going to save. I'm just going to open. Sorry about this. I'm just going to open the project that I've directed you to. So this is the file that hopefully you've just downloaded or you've recreated yourself. If we click the PCB button, it starts up pcbnew. It will ask you the first time you run it whether or not you would like to enable acceleration, and if you don't have the file, it will ask to create it for you. Let's get rid of those. Basic navigation is the same, F1 and F2 to zoom in and zoom out. And the first thing that we do is, under Tools, update PCB from schematic. And that brings in all of our symbols. If we close, so that's all of the parts that we've brought in, and you can see the little lines telling you what needs to be connected where. Before we keep going, on your piece of paper, where's mine? On the piece of paper on the PCB side, there's two dialog boxes. Unfortunately, between 5.0 and 5.1, they've changed these dialog boxes a little bit. I'm going to be showing you on the screen the slightly older version. The newer version has the same things, but it's under File, and I think it's File, and then PCB Setup is the dialog. We are doing a 2-layer with parts on the front-only board. So we select that in the first setup dialog, and that sets the collection of layers that we would like. And then under Setup Design Rules, the design rules essentially specify the design rules reflect the capability of the manufacturer. If you just enter the design rules as on the diagram, we have 0.15, 0.15, and the via diameter is 0.6, 0.3. So these settings that I'm providing are supported by all of the major prototype houses at their cheapest level. If you need finer pitch, you pay more. And what I'm going to do is I'm going to add a second group which I'm going to call AC for the alternating current, and I'm going to make these twice as thick because the AC line has a fair bit of power, and then down here you select the groups on the left and the right and push the parts across as shown. So we want those three push across. You'll notice that the if the net hasn't been specifically labelled, it gets an automatic name. If the net is important, often you label it so that you can find it at this point. And under the global rules, I just need to drop that down. Okay. So I'm just going to do a quick demo, and then I'm going to undo it and take you through it. Okay, so that's the basic process. Now I'm just going to run through that again. Just delete what I've done. Okay, so when you import all of the parts via the tools import, you just get a mess of bits. The first thing that you should do is spread them out a bit and group them up. So for example, C4 goes with U1, so put them together. Just make it a bit neater. What I've pulled out is the parts that go with the connector. And I use M and I move them around. I hit R to rotate them into a position, that I would like. At this point, I'm going to click on this side. There's a whole list of layers. I'm just going to turn off the fab layer because it's not particularly useful and it just gets in the way. So you move the part and you can see the lines coming from the part down. And if I hit rotate, I've got lots of crossed lines, so I just hit R until it looks neat. And then I position it accordingly. Zooming in, to draw a trace, to draw a wire to connect two parts, I press the letter X, and then I click the foot pad, the footprint pad that I want to start with. So I want to connect that pad. When I click on that, you can see it's highlighted, or it masks out the other pads, highlights where it needs to go, and I just run that. Sorry, I was on the wrong layer. So I just run that up. I will cover layers. Similarly, I want to run these down. There's two ways to render that. I'm just going to zoom right in. So there's two ways to run that trace. It can bend it early, like that, or it could sort of bend it the other way. If you press the slash key, it will actually swap between them. So I can do that, and then I can run that back up to the other pad, like that. You do want to be careful not to have any corners tighter than a right angle, because when they do that etching process, the acid can collect if it's too acute. We can also run traces on the bottom of the board. So if I start a trace and I run a trace down, like so, I can press the letter V to put a via in, and that drops a via. It also automatically switches it so that I'm now working on the bottom layer. And the bottom layer is green. And on the bottom layer, I can run it out. These through-hole pads, because they're sort of intrinsic vias, they exist on the top and the bottom layer. So I can run that trace across there. If you're not drawing a wire and you press V, it will switch layers. So connect that there. Finally, for the ground, what I'm going to do is I'm going to put a via, and I'm just going to leave it like that. What we'll do at the end is we'll place a zone, and we'll place a ground zone across the board, and we'll just draw that out over the whole board. And that fills that entire bottom plane with ground, because ground's used in a lot of places, and for a bunch of electrical reasons, having a really big ground is good and useful. What we tend to do is put ground across the entire bottom of the board with that pour. You can see if I zoom in down here, where I put that trace on the ground, it's just drawn around it. So if you are putting traces across the bottom layer, try and keep them a bit short so that this pour works. You should be able to do this board without a single, as a challenge, you can do this board without a single wire on the bottom layer. The reason that I suggest doing this at the end is we can actually, these left buttons control the view, and we can actually, oops, that's the one, hide it so you can see the green box, which is nice, but inevitably if you press delete anywhere, it's going to get rid of that pour, and that's going to happen anyway. So there's a few glazed looks. Does that make...
You need to finish all the underside traces before you do the ground plane?
No. So if you...
And traces afterwards, then the ground plane will magically get out of the way.
You tell it to re-pour itself. You just hit the B button, it re-pours itself and it fixes itself. But as I said, once you put that ground plane down, it's very easy to accidentally delete it. So I would suggest doing it right at the end. But what we can do is we can just drop vias like that in anticipation of the ground plane going in later. There's a lot of glazed looks. I suppose it has been almost an hour. Give it a try. Okay, I'm afraid we've got about 3 or 4 minutes left. I'm sorry there was so little time for the PCB exercise. I didn't plan the timing particularly well. It looked like everyone had gotten the basics of it. It really is a bit like a puzzle. You just sort of push the pieces around until it looks pretty. This is the one that I did, just as an example of how it could look. I'm not saying that mine is good or better or anything like that. It's simply a solution. Would like to show you, there is a command. If you hit Alt-3 or you hit View 3D Viewer, let's just push that somewhere else. Kicad will give you a 3D view of your board. You can rotate it and have a look. If parts have a 3D model, they'll be put on. If they don't, they don't. But it's kind of pretty. Wanted to show you that. The final step, once you've finished your board and you're happy with it and you would like to get it manufactured, is you push the File Plot button. You then can select a bunch of things, and we can say we want it in an output directory called Gerbers, and we push Plot. This produces a series of Gerber files, which are essentially, it's a bit like a PostScript document for each layer. So it describes each layer for the manufacturer, and then we hit Generate Drill Files, and we hit Generate Drill File. It goes in the folder. If you zip that folder up into a zip file, you can go to a manufacturer's website. I'm going to go to JLC PCB. There are a bunch of manufacturers which will do prototype boards for you quite cheaply. I use these guys. Some people say their quality isn't great. For their price, they're phenomenal. Other manufacturers are PCBWay, OSH Park, Euro Circuits. I've used most of them. All of them are fine. They're all much the same. So if we hit the Add Gerber file, and I use the zip file that I prepared earlier, it uploads the zip file. They'll then take that, unzip it, blah, blah, blah. Gives you a nice quick picture. That's their picture. They've generated that. And if you go to the Gerber viewer, this is what they think the board will look like. And it's a really nice sanity check that it looks like what you think it will look like. And you can have a bit of a look there. There's a bunch of different options. So it picks up things like the dimensions. You can select how many you want, etc., etc. The price is $2. That is US dollars. So it's about $3, but that is insanely cheap. Then you're going to pay sort of $10 to $20 in shipping, US dollars, depending how quickly you want it. But yeah, once you've finished drawing out your board, it's as simple as plot, zip, order. And if you are willing to pay $20 for the shipping, they will create it in 24 hours. It will be in your house within 1 week. Thank you very much for coming along. Sorry, quick question? Sorry? It depends. So they give you a few different options. I might just pick it. You don't know why the typing's not working. Let's get the right company. There we go. Australia. $15 to 20 business days is their long shipping. That costs $7. And then, yeah, you can ramp that up to 3 days with DHL.
Thank you, Dave.